after your polyvidiabic step into diffraction, let's formalize a bit, put some notes on it. So you could either have printed the full set of notes originally, you could write this on paper, but you got to write the questions with it, or you can write this, actually type it right into a Google Doc that I've shared with you, get your own copy. Either way, you got to upload your notes when you're done with this. All right, so on page 19, we've talked about a few things waves can do. We talked about they transmit, they absorb, they reflect. We said every time a wave hits a boundary with a new medium, that these three things will all happen in varying degrees. So some of the wave will go in, some of the wave will be lost, energy transferred, and some of the wave will actually bounce back into the original medium. We focus then on one of the transmitted waves of great interest to us. That's the refracted wave. It's when a wave actually hits a boundary, goes into the new medium, and you see some of that bending, etc. So now you learned about diffraction. So diffraction, if we want to formalize, is the wave spreads out. It often looks curvy, although you generally don't see this. The wave spreads out or curves after passing through a narrow opening around a barrier. Or around a barrier, excuse me. So basically, things get in the way and waves can go around them. This is unique. You see the asterisk on there. Diffraction, also interference. We're not up to that yet, though. They're unique to waves only. So Forrest Gump, a wave is as a wave does. If something diffracts, it's a wave. So baseballs, for example, you can't throw them at a barrier and then they sort of morph around the barrier and then keep going on the other side. That sort of thing doesn't happen. So diffraction, however, does happen for sound and light, and you saw some of that. It's pretty neat. Basically, a wave will spread to fill the container that it's in. And the same thing if you have a pool of water. If you tap the water in the corner, that wave will spread out through the entire container. And so that's really what waves do. So diffraction is definitely unique to waves. Let's jump over and get particular with our notes on diffraction. Let's see where we are after refraction. Is that up here? Oh, almost. There we go. What's diffraction look like? Okay, so there's a little simulation, but basically, let me get you to it. So if you're using the Google Doc version, it looks something like this. There are no diagrams within it, so you can just type in the questions, and if you have a printer, you should print it and sketch in the diagrams. You might have done that already, though, with the notes if you had a printer going. Otherwise, you may want to use like a pen function in there and sketch a little something rudimentary for yourself, or maybe just describe it in words. Generator, tank, parallel wave fronts coming toward narrow opening. You could even put the words in the proper orientation. And then over here, other side, and you'll see. So what happens? Basically, you send waves down here. Let's do a little drawing. And so here they come. I'm going to keep this the same distance, the same spacing. Now that spacing is important. There we go. And you'll see why that spacing is important. I could group these two. Cool. So that spacing is important because really that spacing represents the wavelength. So here, if you're doing this in your notes, you try to sketch it with a pen. You don't have to get so perfect as to do this with a ruler. It's fine. But what's going to happen here is these wave fronts, and maybe I'll color them for you. Color, let's have them blue. Why not? Go with our blue obstacle. So these wave fronts are really just waves coming toward, here's a generator, coming towards this narrow opening. And so what happens when it gets to that point of the narrow opening? Well, actually, they get through. And in fact, the spacing is about this, so you're going to have a little piece right here. And we could mark off right here this spacing between wave fronts from here to here, or from here to here. That is what we called a wavelength. So that's like crest to crest. Over here is a wavelength. All right, so what happens? Wave hits a barrier, the part that strikes the boundary. Well, if this is a heavy concrete boundary, for example, of course, three things always happen. TAR, transmit, absorb, reflect. But if this is perhaps a heavy concrete boundary meant to minimize the amount of waves that pass through, well, then this thing actually is going to be pretty effective at reflecting. So you're going to get some reflection. Not writing out the word here, you can write it. Tar with a focus on reflection. So some of the waves actually will bounce back this way. And what you'll see is you'll get more waves coming back now. Oop. These will be offset from the original waves. So they'll hit and then they'll bounce back and start going back this way. So I'll draw these kind of coming back. Maybe I'll dash them and make them red. I know the picture gets a little confusing. But basically the blue waves come in, hit, some of it bounces back. But not all of it bounces back. Some of it passes through that little opening. And then what? Oh, what happens to the part of the wave that passes through the slit? Well, the quick answer is it keeps going. However, it does more than keep going. Keep going is the short answer, but it does a little more than keep going. Because you would probably be surprised. I'm trying to maintain the spacing. You would probably be surprised to see a wave come through and just do this. So imagine this is a body of water. To have this little wave come through, not wide, and stay totally contained like this. So the water stay calm over here and this one piece of wave just come at you. You've never witnessed that because it's not what happens. What happens actually, as soon as it gets through, this wave starts spreading out to the sides. And as soon as it does spread out to the sides, it takes on an appearance more like semicircles. And you want to still maintain that spacing all the way over the wall. So this is still a wavelength. Maintain that spacing all the way over the wall. A little hard to draw. I'll try to get nice semicircles here. So we can modify this answer. It keeps going, comma, and spreads out through the medium. Often you get this semicircular pattern. Circular pattern. Okay. Now, we saw a bunch of examples in the other videos. Let me change this so it contrasts better. There you go. We saw these in the videos. We saw light spreading out. We saw a number of things happen, and sound spreading out. And one of the neat things here is what happens to all these other factors. What happens to the frequency, the period, the wavelength, the wave speed? Well, you know already, right here, we just talked about the wavelength having to be maintained. Let me come down here. We already know that the wavelength has to be the same. So this is going to stay the same. The speed, well, did we change medium? Well, no. And this is a good one to remember. Wave speed depends on the medium. So if the same medium, comma, you get the same speed. Okay. And if that's the case, we have our equation V equals lambda, V equals frequency times the wavelength. So if the wavelength stayed the same and the speed stayed the same, well, then the frequency has to stay the same. And if the frequency stays the same, the period stays the same. So basically, they all remain the same. Fundamentally, the reason is it's in the same medium. It's really what's going on here. If you remember, we had wavelength changing, speed changing. That was a matter of refraction. But here, same medium, that means not refraction. So everything stays the same. The wave just spreads out. Ultimately, what that means is the amplitude is going to drop off. So this wave will get shorter as it spreads. And that makes sense. The energy spreads out over a bigger surface. All right, so here's a note you need. I meant to wipe these down, but whatever, here they are nonetheless. What you should have noticed from the video, the longer the wavelength, the greater the diffraction. This one actually is a real big deal. The longer the wavelength, the greater the diffraction. That's kind of the one quantitative-esque statement you really have about diffraction in this course. So if you noticed, Sound is of a pretty big wavelength. That diffracted much better than visible light, and actually this can help us. Let's go over here. Longer the wavelength, longer the diffraction. We actually saw this really in great detail. So here, check this out. Here's AM versus FM radio waves. If you remember, the AM diffracted better into the garage than the FM did. AM also diffracts better driving upstate into the mountains than FM did. If you look at the wavelength scale, AM is up here on the order of 100 to 1,000 meter wavelength. FM is on the order of 1 to 10 meter wavelength. So you saw the bigger wavelength definitely diffracted better. We also saw that the green laser versus the infrared remote. The infrared diffracted better. Infrared, notice, is bigger wavelengths than green, which would fit right here, this little gray bar. So again, the bigger wavelength infrared diffracted better than the smaller wavelength green light. You saw that because the green laser, you really have to point exactly what you want to hit, like the screw head in the video. But the infrared, the bulb and the TV remote, you could point a little bit away, and it would still work. And of course, we saw the comparison with the radio waves here. All of these qualify as radio. The RC, radio controlled little toy remote. So that one, of course, there, the controller was able to stand behind the fence. You didn't even need to see him. And so that diffracted more than the infrared did and more than the visible light did. So these things were all very obvious. Even down here, the red and the violet. The number part of it wasn't obvious, but the fact that red diffracted more than violet. You saw the red little puff balls we put on there were spread more than the violet. Well, red, you could figure out the exact numbers, but red is over here to the right. Red is really on this rightmost edge of the visible span, and violet's on the left. So this is the bigger wavelength, smaller wavelength. So all the examples we saw definitely at least showed this to be true. The longer the wavelength, the greater the diffraction. Now, whether you get asked these questions, some of you taking this next year will, for slit problems, and we're going to look at a slit problem. This is a slit problem, actually, where you have waves coming toward a narrow slit, and some of you are going to do an advanced double slit one. All of you are going to watch it, though. For a slit problem, it's actually the relative length. So if you want a lot of diffraction, you really want to squeeze the wave through the opening. If you can remember that, squeeze the wave through, you get a lot of diffraction. So that means you want a big wavelength and you want a narrow slit. So the bigger the wavelength, the bigger the spacing over here, and the narrower the slit, the more the wave will diffract on the other side. So there it is. For max diffraction, the wavelength should be much larger than the width of the slit. Here's that little inequality. Now, if waves encounter an obstacle, this is a very similar scenario to what we just did, except there's just a one-sided obstacle, and this happens. This is really not particularly strange. Let's see if we can pull these over here again. Yeah, come on down. Same sort of thing happens as you approach. All right. Oh, these are a little taller. Look at that. Oh, that's okay. We'll overlap on top. Boom. 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 And of course, you see what's coming. The wave is going to hit this barrier. So what happens where it strikes a boundary? Tar! If it's a heavy concrete boundary, well, then you will maximize really the reflection. Not all boundaries are heavy concrete. This could be a floppy piece of plastic, and if it is, it's actually going to maximize the transmit part of it. So it really depends how you create this obstacle. It depends on your intent. You know, if you have something in there that's designed to absorb energy and flex back and forth and act as a generator for some sort of electric device, you're going to want that thing a little more floppy. So it depends what exactly you're doing with this barrier. So of course, you're going to get some reflection, and you saw up above, the wave fronts will come back, and they offset. In fact, they continue to overlap each other. These move this way, these move this way. We'll learn more about that with interference. But the wavelength is maintained. Now, we can cut out. We don't need this blue up here in case anybody's looking at that and feeling confused. That's just because I copied and pasted and they were too long. Okay, so now, what happens to this part up here? Well, you probably know the answer already. Keeps going. Boom. And spreads out through the medium in a circular pattern. It doesn't mean you literally see circles. You may see semicircles. Depends on the shape of the medium and the boundary. So keeps going, spreads out. So I'll try to draw that in real quick. So try to keep the spacing the same. Now up here it's pretty easy. It just passes through. So right about here, and here maybe, and here. Not easy drawing with a trackpad. Okay, but the part that misses the boundary, or the part that is near the edge of the boundary, you would be surprised if you were sitting over here and this water were totally calm and you just saw these waves passing by and maintaining. You'd think there must be some plastic wall, some translucent wall. And so that doesn't actually happen. These will spread out over here. These will spread into this region. We'll look at a couple of pictures of this business in just a second. And so just another comment that's really the same as the above. Waves spread in every direction until a boundary stops them. So wave energy spreads out behind obstacles. And this is why you can't really hide from sound in your house. Somebody makes a sound, there's air everywhere. If you could take all the air out of your room, the sound may not make it to you, but then you might have other problems. So a couple of these, so this slit problem and this behind the obstacle, let me pull up these images. Got them in here somewhere. Where is diffraction? Here we go. These are actually pretty cool. So if you notice over here, we got some notes on this. I'll clean this up so you can just look at this. If you notice, there are waves. Waves are coming in from out here. Now it's a little hard to see. It's a windy day, but there are wave fronts coming toward this situation. Actually, if I look at it, it looks like the wave fronts are roughly oriented, not quite that way, maybe more like this way. Looks like they're coming in something like that. And of course, we're on an angle, so it's hard to really judge. But it looks like the wave fronts are coming in something like this, not this. But what happens over here? Of course, the spacing should be roughly equal. However, an interesting thing that some of you will think about, but most we're not going to have to quantify, is that as water depth changes, the medium actually changes. So when you go from deep to shallow water, as you do as you approach the shore, it is now a new medium. The wave speed changes and the wavelength changes. You go to the beach, you can actually observe this very effectively. Just watch right by the shore, especially low tide. Gentle water coming in. So if you notice, when it comes around here, you're still parallel over here. You still get these wave fronts, but then it curves around the edge. You can see this curving pattern around the edge, not nearly as wobbly as what I drew, but you see this. This goes around the obstacle. So here's waves going around a barrier. And if you were chilling over here in an inner tube, enjoying the not so sunny day, yay, well, you would feel some wave action here. So I'm drawing the profile view. So this is like a crest, a trough, and so on. So the waves would make it around. Another one that's pretty cool is this one down here. You get the wave fronts coming in, parallel roughly. It's rough ground underneath. But they fit through this narrow slit. And then, move these out of the way. You see the waves spread out in that semicircular pattern. Pretty cool, right? So this is that narrow slit. So with light, you don't really see this pattern. You see the effects of the pattern on a wall, which I'll show you when we do the double slit. But here with water waves, it's nice. You can actually see the wave fronts out here and then the wave fronts here curved as the waves go through that narrow opening. Pretty cool example of diffraction right there. Diffraction in action. All right, let's go over here. Let's wrap up what we were just doing. On the back, determine the amount of diffraction based on each. So basically a lot or a little. So the first thing to do here is mark off the wavelength. So here the wavelength is small. Here the wavelength is big. Here the wavelength is tiny. And here the wavelength is, you can't tell. I don't know the wavelength. Why? Because these are rays. So I don't know the wavelength. These are rays. These are not wavefronts. Wavefronts show wavelengths. Rays show direction of wave motion. Now the other thing to note, of course, is the slit. So this one, sometimes they call that slit width D. So this one is small. This one is equally small. This one is large. And this one is the same small as before. And so which one of these is going to have the max diffraction? Well, remember, you really want to squeeze a wave through the opening. So big wavelength, small opening. This one is really max diffraction. Then among the others, small wavelength, big opening. This one is the minimum diffraction. It's not zero, but it's minimum. This one is mid diffraction. Remember, these are all comments on diffraction. And this one is you don't know because you don't know the wavelength. All right. Now, we did a bunch on this in the video, so I'm not really going to talk about it here. But AM, FM, and a cell phone, satellite radio. By the way, cell phone now also, some of the cell phone carriers will use frequencies that get up near this too, 1 to 2 gigahertz as well. Here, what you should notice is that just from this, FM, AM, so this chart you see here is running in the opposite direction to this one here. So AM here is big wavelengths, FM is smaller wavelengths. All of these qualify as radio waves. We're just picking out particular ones. So this is running in the reverse direction. So we got AM, we got FM. Then there's TV fits in there too. Some of your TV is still sent over the air. Not everything has to come through the cable box. So if you have an antenna, particularly in the winter when the leaves are off, aim the antenna in New York City, you'll get some stations. You'll get some free TV. Actually, some of it comes in pretty well. But then there's cell phone and satellite radio. Those would be around here. You know, cell phone, satellite radio, you're just moving down the chart. So those would be more like 10 to the minus 1. All right. So within a medium, frequency and wavelength are inversely related. Of course, that's V equals, you did graphs on that too, frequency, wavelength. So within a medium, the speed stays the same. So if the frequency goes up, the wavelength has to go down, or the reverse. All right. Which color visible light will diffract the most? Well, of course, you want the biggest wavelength. We practiced that already. We did that. The answer was, we talked about it with the PRT2 also. The answer was red. Biggest wavelength, red. There's your answer. Boom. Which radio frequency will diffract the most around large obstacles, etc.? Well, here's all the different radio frequencies that we talk about. Of course, the answer is the biggest wavelength, which is not red in this case, but AM. AM is the biggest wavelength. In fact, it's not a bad idea if you could fit this maybe over here or on the margin. Just a quick little, like, we had gamma, X-ray, UV, visible, IR, microwave, and radio. So we can put the symbols for them, actually. If you copy from PRT2, you should write this over here. PRT2. So we had gamma rays, which is sometimes written like this. We have X-rays. We had UV. We had visible. We had infrared. We had microwaves. That micro symbol. And we had radio. RC, we can call it. Radio. RC means radio control. But what you notice here is as you go this way, you have increasing wavelength. And as you go this way, you have increasing diffraction. Worth writing. So that's why you hear people talking about radio waves, and they're using radio stations and sending signals around the world, and satellites are sending you signals. It's all radio waves. They don't talk about UV rays sending signals around. It doesn't diffract well enough. Radio waves diffract very well. They go around obstacles. In fact, you saw this. We watched a video on this. This is basically the Catskill Mountains. Catskills Very simple drawing, of course. Oh my, I know it's painful to watch me write this, right? You know what this area here is? Over here is NYC. This is not to scale at all. The buildings in NYC are not as high as the Catskill Mountains. But what is in between NYC and the Catskills? Us, EHS. And EHS is part of the, or is within the Lower Hudson Valley. Yes, the Lower Hudson Valley. There you go. Because we are actually at a low point relative to New York City is part of the Lower Hudson Valley too, by the way, but relative to the Catskills. And so what you're seeing here is AM and FM radio waves, and these are all wave fronts. And so from solid line to solid line is a wavelength, and then again from solid line to solid line, and then also from between the dashed. So dash to dash, dash to dash, dash to dash. Those are wavelengths too. Of course, which is which? The little wavelength is FM. The big wavelength is AM. And once you get up to those mountains, what happens is the little wavelength FM does not diffract well, but AM does. Boom, here comes that AM radio. Yes. So when you're riding up those mountains, go about an hour, hour and a half north, you're going to lose your Z100 and all the rest of those. And they are high power. You're going to lose them, but you'll still get your AM radio. Still get your 1010 and your 880 and the rest of that because it diffracts better. That's it. It's not that they have more powerful antennas or anything else. It diffracts better. So it's a pretty neat thing. By the way, this is not to scale. If you notice over here, AM radio in the 100 to 1,000 meter, FM in the 1 to 10 meter, AM radio is about 100 times bigger wavelength. 100 times bigger wavelength. That's a lot bigger. Okay. By the way, why are all the radio antennas coming to you live from the top of the Empire State Building? The people are not at the top of the Empire State Building. The antenna is. You want the antenna on high ground because then it has more line of sight to people in their cars or their homes everywhere around. There are the rays going to them. If you had it on the ground, put the radio station antenna down here, the buildings that are nearby would block the signal. So you have all these broadcasting from the top. They have their antennas. That's hot real estate. Get an antenna on top of a tall building in New York City because then you can reach a bigger audience, literally. All right, cool stuff. All right, most remote controls use infrared. Some use radio control. We talked about those. IR remotes must be roughly. Why? Because the wavelength of radio control is greater than the wavelength of infrared. So this is saying, why must IR aim roughly? Well, whereas RC does not, the wavelength of RC is greater, so it diffracts more. That's it. So this, hopefully, you have a pretty good understanding of what's going on with diffraction. So it diffracts more. Hopefully, you have a pretty good idea what's going on with diffraction now. A couple little things down here you can talk about, read about. One last cool thing to talk about here is cell phones, real quick. You guys are lucky to live in the post-dropped call era. Back in the day when we first had cell phones, around like 2000-ish, and people had them before that, but became more ubiquitous early 2000s. So every time you're on a call, it would just drop. And the way phone companies charge you, you bought like a 160-minute, 100-minute, 200-minute plan, which means you had 200 total minutes of talking that entire month. And every time you made a call, they rounded up. So when you called someone and it rang and then dropped, that was 1 minute. And you would sometimes do that 4 or 5 times in a row. 5 minutes were taken up out of your 200 for the whole month. So people ran over cell phone bills very quickly. Old Biggie song, Juicy, phone bill about 2 G's flat. He's actually talking about spending $2,000 on a phone bill that month. He's not kidding. Phone bills then were crazy because you only had a limited number of minutes and dropped calls, and you would call the company and fight with them and say, no, look, I have 4 calls in a row to the same number, all made at the same time. You get your statement. And so they'd give you some of the credits back. It was a mess. Anyway, the way they dealt with that is just like if you drive north on the Hutch, there's a curve in the road as you're passing by Scarsdale to Mamaroneck there. You haven't gotten to the gas station yet. And they put a big cell tower right there. It didn't used to be there. and that's where calls were always dropped. Then when you're driving past that gas station, near it, there's that big fake tree. Cell phone towers. People are getting them in their yards depending on where they live. Cell phone towers, the only way to really get more cell phone service is to put up more towers. Because if you notice, they are higher frequency, smaller wavelengths, so they do not diffract as well. And that's really the reason you need towers everywhere. All right. Diffraction. Go make your instrument.